Hello, you bunch of aspiring students. Welcome back to the channel, where today we're going over one of the most useful concepts in chemistry, the mole. No, not the animal, the mole, the unit of measurement, as President Me will probably tell you. So, beware, there is a couple of mistakes that I make in this video. I am not taking them out of video because I can't be bothered. Please enjoy the video. And let me know in the comments, how many Pokemon do you see throughout this video? Remember to make notes efficiently, because this is the simplest concept that you can mess up on. But anyway, enjoy the video, enjoy my mistakes, and I'll see you in the comment section to tell me how many Pokemon there were. Hello everyone, and welcome back to another video. Today we're going to be recapping and reusing the concept called the mole. This is used across all of chemistry, most of science. Anywhere you go, you will see the mole. It's one of the most useful methods of measuring how much of something we have in, and we use it in terms of atoms. But anyway, to start, we'll find out what actually is the mole. The mole is defined as the amount, I'm going to write this, so excuse my handwriting, of a chemical substance that contains as many elementary, you don't have to say it like I am, obviously I'm reading it from my script, entities compared to 12 grams, no why I put an S into there, 12 grams of carbon 12. I've put that the wrong place. Firstly, first thing you see when you look at that definition, carbon 12. Carbon 12 is just the isotope of carbon. We use this to compare a lot of values. But all it is our usual carbon that you'll find on your periodic table. Let me get mine up. So carbon with an atomic number of 12, if you can see that just above the shadow. So this definition is great. It's wonderful. It gives us everything we need to know. But how do we use it? Well, we need to know that 1 mole of the substance contains 6.022 times 10 to the 23 atoms. This is the main concept of how we can apply chemistry in terms of substances and physics, for example, in terms of energy of a particle. Now, where do we use the mole? Well, to give it some context, we could show it in terms of atoms, as we've said. So literally looking at how many atoms are in X amount of moles for some substance using this number. Excuse about my dodgy line. Smiley face. And then we can use it in terms of light. So say that's the light wave of a photon, we could find the energy of this wave. So let's put our important notes and our title back on our whiteboard so that we know what we're using. So the main equation you're going to use during your course or during your study when using the mole will most likely be in chemistry, where you're asked to turn the mass or the concentration into the mole. Both of these are very similar equations, which we will run through in a second. I just wanted to show you the units for everything we're going to do in both of these equations before showing you how to use said equations. So firstly, we will start with the mass, because I feel it's the easiest one to remember and probably the most common one to use. So when we are talking about mass, normally we'll be using grams. Sometimes in the question, the question will give you kilograms, so all you need to do is remember to times by 1,000 to go from kilo, which is 1,000, to grams, which is obviously 1,000 times larger than kilograms. So just watch out, make sure you notice which units you're using from the question, because you might have a bit of trouble when you come to our next value, the molar mass. This is sometimes given to you in the question, but 9 times out of 10 it won't be, because the molar mass is literally just the mass of each element you're asked to find. So to give an example, carbon dioxide, all we're looking at is the atomic mass of our carbon and our atomic mass of 2 oxygens, which is 12 plus 16 plus 16, which overall is 32, 44. I think. I can't do basic maths. 44, yes. Now for units, the units are pretty simple, pretty okay to remember. All it is grams mole to the -1. We call this grams per mole. So to think about it in other ways, you could call it grams per mole, looking at it like a fraction. And there is a mathematical link between both of these, which I will just quickly jot down now. I probably won't go into too much detail on it, simply because it is maths and not chemistry, but maths is a pretty big part of our course. So when we look at it, we have our grams and we are doing it per mole. I like to look at it like this, where our numerator is on top of our denominator, as shown in like every other part of maths. And there is an equation that links a fraction like this to our unit. And all it is 1 over x equals x to the -1. This is taught in probably high-end GCSE maths going on into A-level maths. So if you're not understanding it, then that's fine, because it might not be a topic you've learnt about. And even if it's a topic you're not comfortable in, that is fine also. And how you would read it, it is literally just a simple case of going whatever's on the left per whatever's on the right. And this will be the same for the units that we cover soon in the concentration equation is the word I was going for. Now the final variable we're looking for has to be the mole, otherwise what's the point, right? Now this unit is simply just mole. As you can see by here, we don't need to put mole with an E. Chemists and scientists just use mole because A, it's a unit, and B, scientists are very lazy, especially chemists. This is our unit for mole and mole only. Obviously you can have kilomole, millimole. It is just the same as grams and kilograms. So all we need to do is just be careful about whether we're timesing up, whether we're timesing down, like here. So how do we link these then? Well, if you could have a guess, through the units, we've got grams on its own, grams per mole, and mole. So to link this, I like to remember a little triangle, simply because we might end up having a fraction. I'm going to spoil it. We do end up having a fraction. So the one we are taught is mass equals molar mass times mole. So grams equals grams mole minus 1 times mole. Both equations do exactly the same thing. As you can see on the units, something to the minus 1 times something without a minus 1 just cancel out. So if you look at it like 1 over 2 times 2, it just goes to make 1, because all this is doing is just cancelling out to give you 1. Another way I like to remember it by is a triangle. I've always learnt by the triangle. I will be caught dead if I'm not using a triangle. So all it is again is just mass, molar mass, mole. It's a very large triangle, I'm aware. Stick with me. Now how I use this triangle is the way that you might not have learnt how to rearrange equations or however. Essentially, it's a very simple method. All you do is, for instance, we are looking to find the mole. So all I would do here is, using my hand, I would cover up the mole and write that down. Obviously, we're looking for the mole. So by covering up the mole, we then have mass on top divided by our molar mass. And we get the same by rearranging the top equation. So divide by molar mass on each side. We will still get mole equals mass divided by molar mass. So both techniques work. Use whatever you're comfortable with, whether it is rearranging equations or a triangle. No one discriminates about drawing a triangle as long as it's not obnoxiously large. People might get confused. But this is the equation that you guys will learn anywhere in chemistry, whether it is standard rearranging equation or cover up, write it out, however you guys wish to do it, perfectly acceptable either way. Now this is exactly the same for concentration. There's no real difference except we're not using mass and molar mass. Instead we're using concentration, volume, and mole. So obviously moles have the same value, same unit. It's just concentration and volume which might have a different unit. So volume is normally you're given it in either centimeters cubed or meters cubed, but the way we use concentration in this instance is we change it into decimeters cubed. And the reason for this directly links to concentration, as normally concentration is given in mole dm minus 3. Again, with this minus, it's nothing new. All it is 1 over dm cubed, which is the same as 1 over 2 cubed times 8. These are exactly the same thing, so these two cancel, giving us 1. So normally we're given concentration in decimeters cubed, but with volume, just need to be careful about your timesing up and timesing down. There will be a video of how to go from centimeters cubed to meters cubed, and similarly centimeters cubed to decimeters cubed. That will be coming out hopefully within the next couple of days. So the equation, as I said before, is exactly the same as the grams and the mass. I said the same thing, the mass and the molar mass equation, except we are substituting our mass at the start with our moles. So our moles is equal to our concentration, and we are timesing it by our volume. I'm just going to put vol there because I've run out of space on my whiteboard. So our units, mole is mole. Our concentration unit normally is mole dm minus 3, and in this instance we're going to use dm3 for volume, just again to show that both of these, when times together, both units cancel to give us mole. If that's the way you want to remember how you work out your units, completely fine, it's completely valid. So to show you the triangle as the final part of this section, I'm going to label concentration as C and our volume as V, because simply I haven't drawn a big enough triangle. So our moles is at the top, similarly to our mass. I don't know why that troubled me. So all it is going to be C and V at the bottom. And again, the same technique as we did with the first triangle. If you want, let's say, volume, all you're going to do is cover up the volume. I'm going to write down vol equals mole over conc, which, as you can see, would be exactly the same as all we're doing is dividing by C, gives us volume on the end, and mole over C on our equation. So as I said at the start of this video, we can link concentration, moles, volume, mass, mR to energy. If you wanted to find out the energy of a mole of something, you would find the energy and spelling of the energy of question mark and then times it by our magic number, Avogadro's number. Now our energy calculation will be done in a separate video also, simply because the energy calculation is 100% necessary, but in terms of completing the video, I will show you. So to find the energy, you will need to do so this can be used to find the energy, which is covered during a physics module during a foundation course in uni. It also might be covered during A-level physics. So this is one application of how we can use the mole. So we start off by recapping our energy of a mole of photons equation, which we will cover in another video. So I will just write it down. E equals H times V. If you remember from the first video, I used this calculation during an exam style question. That video is more focused on exam technique. So I did use it during that video, but we will dive into this equation some more later on. And all we're going to do is we're going to times this by our Avogadro's constant, or our mole, to find the energy of a mole of photons. And to break it up, this finds the energy of one photon. To make it very clear, one photon is this. So our E is the energy of one photon, and then this gives us a mole of photons, as discussed in the start of the video. And the units of this are in kilojoules per mole. So our energy would be in kilojoules as normal. Standard unit for energy is kilojoules, and then per mole. And then again, linking to standard units, this could also be written as mole to the -1, but examiners aren't picky in most cases. So write whichever one you feel comfortable with. They both mean literally exactly the same thing because of math. So there we have it. That's all the mole is. That's what the mole is. That's how us chemists use the mole. And just remember, to find out any find out anything to do with mass, concentration, volume, our atomic masses, of a molecule. So if we have O2, instead of using 16, we'd use 32 instead, because there's 2 of them. So if you're looking to find any of these, and you have 2, and you have your moles, and another variable as discussed in our triangles, you can find pretty much whatever you're looking for. The final thing that we have to do is, when finding the mole, you have to be careful about equations. So different equations will have a different balancing number. So this is going back a long time to balancing equations. So all I'll do is I'll balance this equation. Oh my god. Why can't I remember the equation of ammonia? Why? It's the Haber process. I remember. So the Haber process H3. Oh my days, what's wrong with me? One of the most famous processes in the world. If we didn't have this process, we probably would not be living. This process saved a lot of lives during the end of the World War II, as it essentially made a really useful fertilizer in farming. Anyway, back to the topic. As you can see, we have a problem, because if we find the moles of this and the moles of this, we're going to have an extra nitrogen left over on our reactant side, if you want to call it that, and we have a missing hydrogen. So physically, we can't make this. We have to add more for it to be equal, for it to stay in dynamic equilibrium, to be reversible. We need to have an equal number of each molecule on each side. So all we can do is simply make these numbers balance. So over on this side we have 1 nitrogen and 3 hydrogens. On this side we have 2 nitrogens and 2 hydrogens. So to sort of make this easier, we're gonna look to balance the numbers. So on this side we have 2 nitrogens, so we need to make this side 2. But obviously in an equation you can't just do one thing to one side, you have to do it to both. So this means we now have 2 NH3s, which gives us 6 hydrogens. And all we've done, simply because we've doubled this, we need to double this to make these two equal. 2 nitrogens and 6 hydrogens. But now we have a problem again, because we have 6 hydrogens here and 2 hydrogens here. The solution to that is having hydrogen on this side completely separate to our other reactant. So we can increase this one to match our product, what we need. We can increase this without it infecting this or without it affecting this. So all we can do is simply times this up by 3 to give us 6 hydrogens. And now look, we have 2 nitrogens, 6 hydrogens, 2 nitrogens, 6 hydrogens. We have a balanced equation. So now when you're finding the moles, we need to take a keen eye to these numbers. If we didn't have these numbers, we would not be able to calculate a proper mole. We'd be able to calculate a proper mole for this one because we have 1, and that's simply following the same process as before. Mass equals mR times mole, mR being our molecular mass. We can simply just do that because there's 1. But let's say, for instance, we didn't have the mass of this. We can go about finding the moles for this and say, for instance, this would be 1. We don't have anything else for this. We only have the atomic mass. So what do we do? Well, as I said, we increase the number of our hydrogens to make it even on this side. Well, that means we have to increase the amount, which means we're going to have more of it, which means we're going to have more atoms. Therefore, overall, we're going to have more moles. If you like to think of it that way, if we increase one, we have to increase it everywhere. So we haven't increased this one, and this has no number in front of it, so we can just keep this at 1. Whereas we have increased this value because this isn't a 1, and we have increased this value because it isn't a 1, it's a 2. So when we look at all of our moles, we're going to have 3 times as many moles here. We're going to have 2 times as many moles here, because this one's a 1, this one's a 2, this one's a 3. We're going to have double the moles here than here, and we're going to have triple the moles here as we are here. So whenever you're looking at moles and you're looking at an equation where you have to balance your equation, please, 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 please take into account the big numbers at the front. And if there isn't a number, that number is 1. That's it for the mole. That's all the information I have for the mole. If I've missed anything, please don't be afraid to shout at me in the comments. I'll try to take it as personally as I can, if I can English. If you have any questions, hit me up in the comments. I'm always checking, don't worry. And yeah, have a good rest of your day.